Bonjour. Uh, so yeah, another topic for limits that's really important. That's used in the introductory level is the idea of the squeeze theorem, and and really what this is conceptually is it's when you have a function that you're pretty sure the limit exists. You're like, all right, like there's some like finite limit going on here, but you're trying. I can't seem to cancel something out. I can't seem to, figure out what it is. Is if you know that it's bounded by two easier functions, then when the two bounds converge, you squeeze like the limit in a sense. Like you're like, okay, I know the limit of this must be A, and the limit of the lower bound must be A, therefore the total thing must be A. So to write that down in words, so it's the idea when uh you know that um when L equals the limit of x approaching A of g of x, and that's also equal to the limit of x approaching A of some other function h of x, where these are the bounds of the function we're interested in, where g of x is less than or equal to uh, our function f of x, which is less than or equal to h of x in some, open interval near this containing this point A, then that means if we have a really hard time finding that, we have a really hard time finding the limit of x approaching A of f of x, then we use its bounds. We use the fact that that must be less than or equal to L, but it also must be greater than or equal to L. So therefore, we conclude that it just equals L. It equals that point. It equals that limit. And so like that's why it's called the squeeze theorem. That kind of gives you the intuition of what you're doing is you find these two functions that 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 you're squeezing really close, and you're saying therefore like our limit must be this because its upper bound is that and its lower bound is the same thing. And so I just want to give like an explicit example of that. So often like we're gonna use like the squeeze theorem on is like your sine or your cosine. You know that those are just alternating um uh between 1 and -1. Um and so if I have the function f of x equals, let's say, x squared times sine of 1 over x, and I say what's the limit of x approaches 0 of this. And so immediately you're like, okay, like it's not gonna be like infinity because we know that like the sine is bounded, and that x squared part, like that's going to 0. So like we're pretty sure like this is just gonna be 0. And so it might be hard to just show that explicitly. Like we have a good feeling that like okay, like this limit is it's a finite number, but it's hard to show. And if uh yeah, because if you put direct substitution, you have 0 multiplied by, and then this is sine of 1 over 0. Well, it's not quite the same as having 0 over 0, because this sine of 1 over 0, that's that's a bit more of a mess. That's be the same thing as saying what is the end behavior of sine? Well, it's just going between 1 and -1, and it's not hovering anywhere else. It just keeps repeating the exact same pattern. So that limit does not exist. So we know right here, like it's like if this was on its own, we'd say the limit does not exist. If this was on its own, we'd say the limit was 0. So, that's kind of hard to reconcile these two things together. And thus, that's where the squeeze theorem comes in, because we know that sine of anything, sine of theta, is less than or equal to 1, and it's greater than or equal to -1. And so since here our input is 1 over x, that must also be true. So sine of 1 over x is bound between 1 and -1. It can't fall outside of that. And so this is where we create those functions g and h, is because we know the bounds on sine. So all we're just going to do is keep this bound and just throw like multiply in x squared so that we get this middle function to be our f, our function of interest. And so we have negative x squared is less than or equal to x squared sine of 1 over x, which is less than or equal to x squared. And now we can take the limit of all the sides. So the limit of x approaching 0 of negative x squared is less than or equal to the limit of x approaching 0 of x squared. Or I'll just say this is our f of x. That way we don't have to keep writing it down. Of our f of x is less than or equal to the limit of x approaching 0 of x squared. But these two ones are really easy. What's the limit of negative x squared? Well, that's just 0, because that's just the parabola going up at the point 0. Same thing with this one, going down to 0. So we know that this must be greater or equal to 0, but it also must be less than or equal to 0. And so that's where we're squeezing the answer out. So therefore, our limit must be 0. And so that's really the idea that that you're going to be using the squeeze theorem in this class. It's really just when you know that there's kind of like some obvious bounds. And so a really obvious one is sine. So that's why I kind of illustrated this, is when you see that you have some ugly looking sine thing and you're pretty sure the limit exists, well, try out squeeze theorem, because you know that sine is bound, and then from that you can create like these function bounds, and yeah, and so that's really the main idea with squeeze theorem. Hope that helped.